the topic our group will talk about is GivBERT, a novel visual entailment approach with global visual information. First, I will talk about I will introduce some background knowledge about our topic. The vision and language task is the integration of CV and NLP tasks. It has shown many interests as the development of the individual of them. And the visual entailment VE is just one member of it. It is originally from textual entailment TE. The task of TE is that given textual premise P and the textual hypothesis H, we need to determine whether H implies P. In VE, however, the textual premise P is replaced by an image premise. The output of TE and VE has three classes: the entailment, neutral, and the contradiction. The traditional architecture of VE usually contains two branches. The first branch uses CNN to extract image features, and the second branch uses RNN or LSTM for textual hypothesis. Recently, a BERT model has been proposed by Google. This is a very revolutionary model in NLP tasks. It uses mask tokens and self-attention mechanism in pre-training stage. This enables the bidirectional understanding of the model. And inspired by BERT, a ViewBERT, which is short for Vision and Language BERT, has been proposed. The ViewBERT model contains two BERT-style architectures for both image and textual branches, and each of them has a series of transformer blocks. And also there exists a co-attentional transformer layer between the two branches, enabling the information exchange between the two branches. The ViewBERT has effectively improved the performance of various vision and language tasks, and the detail will be talked about later. Next, I'll talk about some of the related work. One similar work as VE is VQA, which is short for visual question answering. The task of VQA is that given an image and a natural question of the image, we need to provide an accurate answer to the question. It is usually less challenging than VE because no neutral label needs to be considered. And another similar work is called automatic image captioning, AIC. The study of AIC has a long history, which can be dated back to at least 2004. The challenging thing about AIC is that it requires generative model instead of discriminative model, which requires very large data sets. But the good news is that a data set called conceptual captions has been constructed. This data set contains more than 3.3 million examples. This huge data set has not only been used in AIC tasks, but also be pre-trained to be used in other vision and language tasks. Next, I will talk about the data set we use in our study. We use the SNLI VE dataset. This dataset is constructed from the combination of Flickr 30K and SNLI. The Flickr 30K is a dataset that contains 31,000 images from Flickr, and SNLI, which is short for Standard Natural Language Inference, contains more than 570 human written English sentence pairs labeled by entailment, neutral, and contradiction. This is originally used in textual entailment. And the combination of the two is that the textual premise in SNLI are replaced by corresponding images in Flickr 30K. Next, I'll briefly talk about some baseline results from the SNLI VE dataset. Here is the table of the results. The EVE image and EVE ROI are from the original EVE model. The GivBERT and GivBERT MT are the results from our code. The GivBERT is the model pre-trained from conceptual captions, and GivBERT MT is the GivBERT model further trained on 12 other different datasets.
Okay, so in the next section, I'll talk about GivBERT and its related experiments. So GivBERT, which is based on BERT, is designed as two-branch architecture. One branch extract the image features ahead of time to bootstrap the vision and language experiments. So normally we use faster RCN-based model to extract the image features. Another branch extract text features with the first several K-standard transformer layers. The co-attentional transformer layer merges two branches and make the embeddings from two modalities to be aware of each other. The co-attention mechanism in GivBERT model is actually modified from self-attention mechanism in BERT model. In BERT model, query and key are used together to compute the attention score. Those scores are then considered as the attention weights and applied to values to compute the final attention output. What is different from GivBERT and BERT in co-attention mechanism is that for GivBERT, Q and KB are from different modalities to fuse the features from each other. GivBERT-based visual entailment model leverage GivBERT to generate the image and sentence representation from two modalities. The embeddings of the first token from each modalities are selected to be the final representation and then multiplied together. A multi-layer perception follows the GivBERT model is used to predict the final output. Because the image objects don't really have the natural ordering, we introduce location embeddings for image representation. So here we show an illustration of how we made the 5D location vector. This location embeddings is to indicate the spatial relationship between the image tokens. Moreover, we also introduce positional embedding for text representation to differentiate the words in different positions of the sentences. The alignment between image representation and text representation is vital. So, how the location embeddings and positional embeddings affect the task performance is very interesting to be explored. In the experiments, location embeddings and positional embeddings are removed from the baseline models. So here we list all the experiments we did before. From the results, we can see like for location embeddings, for vanilla GivBERT model, actually after removing the location embedding, the performance drops a bit. But when it comes to the GivBERT model, which pre-trained on 12 more datasets, actually the performance didn't change a bit. So we kind of want to conclude that so more training data is, the less dependent the model rely on the location embeddings. Also, for this kind of spatial knowledge, we think it could be learned from other tasks, which is a mixed model to be less rely on the location embedding. And for positional embedding, from the results, we can see that for both two baseline models, actually after removing the positional embedding, the performance dropped a lot. So we can say so positional embeddings actually are very important feature for text representation, and it is difficult to learn from other tasks. And here it comes to be a problem, which is, although the location embedding is not really hurt the performance a lot when we removing that, but is it the location information enough to represent the structural information of the whole image? And the answer is probably no.
GivBERT integrates both coarse visual information and text information into one single model, which leads to great success on visual entailment tasks. However, the visual features extracted by GivBERT only contain local image representations inside bounding boxes, which leads to deficiency of global sync semantics and fine-grained mutual positional information. As shown in the slides, there is a man riding a horse. In GivBERT, there are two visual inputs. One contains the coordinates of the red bounding box surrounding the man and the corresponding pixel information inside it. And the other one contains a purple bounding box representing the horse, which are both obtained from faster RCN. Although it's true that we can figure out the principal objects on the image, it's hard to know their relative relationships. For example, instead of riding the horse, if the man is standing on the mound in front of the horse, the detected bounding boxes of both the man and the horse will be almost the same. And due to the classification strategy, the mound is very likely to be considered as background, thus has no corresponding bounding box coordinates and the object's information inside the boxes will be rather similar. Thus, it becomes very hard for GivBERT to distinguish their differences, which leads to unsatisfying performances. To deal with this problem, the model needs to be able to reuse the whole image and understand the object's connections. For instance, as shown in the slides, the model needs to not only consider the man and the horse as separate objects, but also have the chance to treat the two objects, that is to say the man and the horse, as one single entirety, and the capacity to observe the whole environment's details is needed. To make this possible, we introduce a new branch to the original GivBERT's visual branch to extract the image's global semantics, which in detail is implemented as an image classification network. We use the corresponding raw RGB image as a branch's input, and then the training set, we apply cropping and random horizontal flipping sequence for image augmentation. And on both validation set and testing set, we apply resizing and center cropping sequentially. In the end, the input image will be normalized with the mean and variance on the ImageNet. Due to GivBERT's massive requirements on both computational power and GPU RAM, it is unrealistic to make the additional branch very big. However, if the new branch's capacity is too low, it may not be able to bring useful information to the model. Based on such a consideration, as shown in the slides, we adopt MobileNet v2 pre-trained on ImageNet as a feature extraction network for better trade-off between the speed and accuracy, which is followed by two fully kinetic layers activated by ReLU function for better fusion with the original network. The final question is where the global information should be fused into, because it is almost impossible for us to retrain or fine-tune the whole GivBERT model due to the limited computational resources. We can only freeze the front part of both GivBERT and the newly introduced feature extraction module, and only learn the parameters of fully kinetic layers following the feature extraction module and the left part of GivBERT. To minimize the parameters need to learn, we need to put the insertion point as back as possible. However, if it is too close to the output, it will be hard for the two branches to merge well. In this paper, we choose to add the global semantics information to the original local features extracted by GivBERT by direct element-wise addition after finishing co-attention operations, because this can both avoid breaking the learned GivBERT's main structure, which is rather hard to train, and gave the BERT ability to digest the external information with the following MLPs. We call this new network GivBERT. That is, GivBERT with additional global visual information. In GivBERT training, we inherit most of the settings in GivBERT. However, due to the newly introduced global visual information extraction branch and raw images massive requirements on GPU RAM, the batch size is reduced to 130 on one single RTX 2080 Ti GPU. The introduction of global features can help the model to synthesize and utilize the image's information on different scales, which promotes its ability to understand the whole thing's semantics meaning. As shown in the table, the newly introduced global information can bring as much as 0.54% improvement to the vanilla GivBERT trained on single task and 0.07% improvement to the vanilla GivBERT trained on multiple tasks. The reason why we can see more significant promotions in a single task case should be that, first, in the multitask case, the model has already seen a great amount of different training data. Thus, the new introduced information cannot act as the dominating factor. And in the multitask case, the model is harder to converge. Thus, need more epochs and a longer time to converge, which is impractical for us due to the computational resources limitations. And in the multitask case, the gradient is more unstable, thus need larger training size, which is intrinsically contradicted with additional global information module. As we demonstrated before, our introduced additional global image features can bring significant advantages to the visual entailment task. In our experiment, the improvement can reach as high as 0.54% comparing with the baseline model. However, it might not be enough to only introduce the global features into consideration. We believe that it is promising to continue fuse information in more scales and integrate some additional information in the earlier stage of the whole network. What's more, we notice that it is always hard for researchers to determine the detailed network structure, especially for the big ones like BERT and transformers. We deeply believe that applying neural architecture search on visual entailment tasks is a promising approach to this problem.